All right, section 2.3 is on measures of central tendency. So measures of central tendency are values that represent a typical or central entry of a data set. They're really used to represent the center of the data or the middle. And the most common measures are the mean, the median, and the mode, although the mode doesn't necessarily measure the center of the data. So let's start with the mean. So the mean is the average, and the way that we calculate it is we add all the data entries. So remember from before, sigma in math means sum. So this is a capital Greek sigma. So we sum x, and x represents the data. So again, this would usually be written with an x sub I, where x1 is the first data value, x sub 2 is the second data value, and x sub n is the last data value. And we would sum from I equals 1 to n, x sub I. But they just use shorthand in this textbook. So we're summing all of the data entries. Each data entry is an x. So we're summing all of the x's, and then we're dividing that by the total number of entries. So whenever we talk about a population parameter, so remember it's a population parameter is a descriptive value for the population, we always use Greek letters to represent that. So the Greek letter is always going to be for the population, and for the sample, we always use a regular letter, okay? And sometimes we put little funny symbols on top of those letters, but we always use just a regular letter. So this is the Greek lowercase letter mu. So this is a Greek lowercase letter mu, and you notice it looks like a U sort of with this extra line on the left side. So what this says, the population mu is the sum of the x values divided by n. And they use a capital N here because whenever we talk about the population, we use a Greek letter for the parameter and a capital N to represent the number of people or the number of data values, the number in the population. Okay, that's the total number in the population. And then for the sample, we pronounce this x bar, because there's a bar on top of the x. X bar is the sum of those data values divided by the total number in the sample. And we always represent the sample the sample size, the number in the sample, by a lowercase n. So again, the population mean, it's the same formula basically, right? But the population mean is represented by mu, and it's the sum of the x's over the number in the population. And for the sample, it's represented by x bar, and it's the sum of the data values divided by the number in the sample. The median is the value that lies smack in the middle of the data when the data is ordered. So to calculate the median, we always first have to order our data, and then we look for the number in the middle. Now, a cool thing, since I have you guys use Excel for this class, Excel will calculate the mean and the median for you without you ordering the data or doing a sum or anything. So I'm going to show you how to always use the formula, plus how to do it using just an Excel formula. So how to do it using this formula, how to sum the x's and divide by n, but then also how to use the formula that Excel has to calculate the mean. So the same thing with the median. I'll show you how to sort it and find where the median lies, but also how to use an Excel formula that just spits the value out for you. So what we do is we order the data set, and if we have an odd number of entries, the median will be the one right in the middle. So for example, if we have 13 values in our data set, the median would be the 7th value, because when we look at the 7th value, there are 6 values below it and 6 values above it. So it totally splits the data in half. But if I have an even number like 12, then to get the median, I would take the 2 numbers in the middle. So I would take number, I have to think about it, number 6 and number 7, because there are 5 values below number 6 and 5 values above number 7. Make sure I did the math right. 8, 9, 10, 11, 12. Yep. And 5 values above number 7. So then I would take the average of the 6th and 7th value to figure out what the median is. Okay, so if there's an odd number, it's the median of the 2 data values that fall in the middle. And then the mode is just the data, the number that occurs with the greatest frequency. So it's the data entry that occurs with the greatest frequency. So if no entry is ever repeated, that means there is no mode. And let's say that most of the numbers appeared once or twice, but you had 2 numbers that appeared 3 times, then those 2 numbers would both be the mode, and we call that bimodal. If I had 3 values that occurred 3 times, and 3 times was the most that anything occurred, then I would actually have a trimodal data set. So there can be 0 mode if nothing repeats, there could be 1 mode, or there could be more than 1 mode. All 3 of these are described as a typical entry of a data set. The advantage of using the mean is that it takes into account every single value of a data set. The disadvantage of the mean is that it's affected by outliers. So if there's a data value that's way off from the rest, it's gonna use that. So for example, if I'm looking at the mean house price, that's why house prices are almost always reported using a median. If I'm looking at the mean house price for my area, this is really crazy. I live in a townhouse, but not very far away from me, literally like, I don't know, maybe a 1/10 of a mile from me is this huge giant house on a lake that's surrounded by water. The way the lake curves, it curves around the house. So it's actually surrounded by water on 2 sides, and it has this giant yard, and it's way bigger than anything else anywhere around it. Okay. That house is, let's just say it's worth $2 million. But then the rest of the area is all townhouses. So maybe the median value is 200,000. So you can imagine that if you calculated the home values, the average home value of the area where I live, which is almost all townhouses, if you did the median, it's probably about 200,000, maybe less, but I'm just saying, I'm picking a number. But when I stick that $2 million home in there with everything else, it's going to pull that average up by a lot, depending on how many houses I use, and make it look like the houses are a lot more expensive where I live than they are. So that's what it's saying when it says they're affected by outliers. An outlier is a data that's like a data value that's really different from everything else. Okay. And again, this happens a lot with home values, but it could happen with other things as well. If you're looking at heights, but then you stick an NBA basketball player into the mix. Okay. And you're looking at heights, and you have, especially when you have a small group of people, the smaller that the data set is, the more affected it's going to be by that big number, because there's not enough other data in there to pull the average back down. But if I look at the median, that value is just my largest one. So it just counts as being in the upper half. So that's why the mean is affected by outliers, but the median is not, because it just looks at the middle. So something at either end, either pulling it, something that's way lower than it should be. Like if you had a little person, and you were looking at heights and you only had 10 people, a little person or a very tall person is going to make a big difference in the mean, but it won't affect the median, because the median is just when you line the people up, the person in the middle is your median height. Okay. And we can also calculate a weighted mean, and that's the mean of a data set whose entries have varying weights. And this is most often used for like things like GPA. When you calculate the GPA, some courses are worth 3 credit hours, some courses are worth 2 credit hours or 1 credit hour. So we have to weigh based on the number of credit hours that each course is worth. So, so to calculate the mean of a weighted data set, X bar is the sum. We take X times its weight. So the value of the data value times its weight in the case that I gave of GPAs, the weight would be the number of credit hours. And then we sum up all of the credit hours or all of the weights, and we divide by that. So if you're taking, let's say you're taking 12 credit hours and you have 3 3-hour courses, and then you have a 1-hour course and a 2-hour course, the weight would be the number of credit hours that each course is. And then you would take your grade value, an A is worth 4, a B is worth 3, a C is worth 2, a D is worth 1. So you would take, like if you got an A in a 3 credit hour course, you would take 4 times 3 credit hours, and that course would count as 12. And then it would be 3 times 4, and that would be 12. If you got a B in another one, that would be, or say you got a B in 2 of them, that would be 3 times 3 is 9. You would have that twice, so you would have 18 for those. And then you got an A in the 2-hour course and a D in the 1-hour course. So the 2-hour course would be a 4 times 2 or 8, and the 1-hour course would be a D, which is worth 1 times 1 is 1. And when we add those all up, we would get the 12 plus 9 plus 9 plus 8 plus 1. And then we would divide it by the total number of credit hours we're taking, which is 12. To calculate the mean of a frequency distribution, we're going to take the sum. First, we're going to multiply each X times its frequency. X is the midpoint. So this is why I was saying if we don't have the data values, we basically assume that every value in a class is the midpoint. So we take the midpoint times the frequency of that class. We multiply those together, and then we sum all of those. So we sum all of those values, and then we divide by the total number of data points, which is the sum of the frequencies. So this is how we calculate the mean for a frequency distribution. So what we do is we find each midpoint. Remember, we already did this. We take the lower limit plus the upper limit divided by 2. Then we would create another column where we multiply that midpoint times the frequency column. And then we sum all of our frequencies. And then to calculate our mean, we take the sum of those X times F, that column. So we take the sum of that column and divide it by N. So when we do this in Excel, it'll make a lot more sense. You guys will see it. Then our distributions can have different shapes. So if the distribution is symmetric, remember symmetric means that it's like a mirror image, right? Symmetry always means like a mirror image. So a symmetric distribution would mean that I can draw a vertical line right down the middle, and the right side of that vertical line is a mirror image of the left side of what's on that vertical line. So you can imagine I could fold this paper in half, and these are going to lay perfectly on top of each other. This is a symmetric distribution. And in a symmetric distribution, it's hard to see here, but the mean and the median and the mode are all in the middle. The mean, median, mode are all right here because these values occur like 39 times. Right, both of these in the middle. 8, looks like it's maybe 8 and 9. Yeah, 8 and 9 each occur 39 times. So the mean, median, and mode are all 8.5. Right, a uniform distribution means that all of the classes have equal or approximately equal frequencies. And the only time you really see this type of distribution used is for deliveries. So if you're looking at like deliveries of a UPS driver, every interval of time, it's equally likely that that's when your delivery will be made. They make usually like a certain number of deliveries an hour, every day. It's pretty uniform. Okay, so that's called a uniform distribution. Left skewed. So be careful here. You might think this is right skewed because the data looks like it's piled up on the right, but the skewing is based on left skewed means negatively skewed. And that's because of having values that are quite different from the mean. Okay, so the values that are quite different from the middle of the data are way out here to the left. So this is left skewed, and this is called the tail. So it pulls this tail out toward the left. So the tail of the graph elongates toward the left. So the tail is where it gets like skinnier, where the frequencies decrease. So this one elongates toward the left. And what happens then, remember, these values that we have, these small values that we have extra of, are pulling our mean that way. So they're pulling our mean out to the left. So what happens is the median is here in the middle. The mode will be to the right of the median, because the median is in the middle of the data, and because of these values, that's moved over from where this highest data point is. So the mean, and then the mean is pulled into this elongated part. So the mean will be less than the median, will be less than the mode. So for a left skewed distribution, the tail is to the left, and the mean will be elongated to the left, and the mean will be less than the median, which will be less than the mode. Right-tailed distribution is positively skewed, so the tail elongates out toward the right. And what happens here is that the mode is less than the median, is less than the mean. So the mode ends up to the left of the median, and the mean ends up to the right of the median. So remember, the skewedness is which way it pulls the mean. All right, so that is the end of section 2.3. I'm going to go ahead and talk about section 2.4, and then we'll go in and do the homework for both of these sections together. So section 2.4 is measures of variation. So there are many ways we can measure the variation. So the first one is the range, which we already talked about. The range of the data is just the maximum value minus the minimum value. So the data has to be quantitative for the range to make sense, but we just take our maximum entry minus our minimum entry, and that is the range. And it does tell us something about how spread out the data is, but it's not really very useful because it only tells us how spread apart the data is, and it's definitely affected by having a larger value or a smaller value, right? A larger maximum will make the range bigger, a smaller minimum will make the range bigger. So just having that one number change makes a big difference in the range, but it's the advantage of it is it's super easy to calculate. Okay, next, the deviation, variance, and standard deviation. So the deviation is the difference between a data entry, a single data entry X, and the mean of the data set. So for each value, each data value, we can take that data value and subtract off the mean mu for a population data set, or the mean X bar for a sample data set. So we take the X value, the data value, subtract off the mean, and that's that data's values deviation from the mean. So it's deviation from the mean. So that's what deviation means. Okay. So to calculate the variance, we sum up all of those deviations. So what we're going to do is create a new column in our data set that is the X value minus the mean. And then we're going to create another column, or you can do it all in one step, but I like to create one column that's X minus the mean, and then another column where I square those values. And then we're going to sum the squared values. So that's why it's called sum of squares. And also denoted SSX, the sum of the squares of the X values. So we're going to sum all of those, and then we're going to divide by the number in the population for the population variance. Again, population parameters. So this is a population parameter, the population variance. Population parameters are always denoted with Greek letters. So this is the lowercase. I know this is confusing, guys. Lowercase Greek letter sigma. So this is the uppercase Greek letter sigma, and this is a lowercase Greek letter sigma. And so the variance is always represented by something squared because we're squaring here, okay? So sigma squared, that's how we represent the variance. So just like this is a symbol we use to represent the mean, this is the symbol we use to represent the variance. So sigma squared is the sum of the squared deviations divided by the number in the data set n, in the population data set, that's capital N. And then the population standard deviation is denoted by sigma. The reason the variance is denoted by sigma squared is because what we really like to use in statistics is the standard deviation. The standard deviation is very useful. We use it for all kinds of things. And so the standard deviation is the square root of the variance. So we take the square root of sigma squared and we get sigma. Okay, so that's why we represent this by sigma squared. So sigma is the square root of the variance. So you'll calculate the variance, then take the square root. Again, we're going to do this in Excel, so I'll show you how to do it using this formula, but Excel has built-in formulas to calculate the variance and the standard deviation for both the population and the sample. And our goal, as I mentioned in when I did the live session on Wednesday, our goal is always, or sorry, in the first class, when I did the live, when I talked about this live in the first class, our goal is always for you to be able to figure out what formulas to use and what you're supposed to be calculating. So you can calculate this. I'm going to show you 3 different ways, one using this formula, and then one using or I guess 2 ways, one using this formula and one using the built-in formula in Excel. And you can solve it however you feel more comfortable, okay? Because I just want you to figure out, like, hey, they're wanting me to calculate a variance in this case, or hey, I need to get the standard deviation, and be able to get that. That's what would happen in real life if you needed to do statistics. So to find the population variance and standard deviation, we would first calculate the population mean, which is denoted by mu, which is the sum of the x values divided by the number in the population, the sample size. And then we would find the deviation of each entry by taking that mean and subtracting it from each value in the data set. So we'll create a new column that's x minus mu. And then we're going to square each of those. We're going to create another column that's all those values squared. And then we're going to sum that column. So we're going to go to the bottom of that column and just sum those all up. And that's where we get this sum of squares. And then we're going to take those sum of squares. We're going to divide it by n. And that gives us the variance sigma squared. And then we're going to take the square root of that. And that gives us the standard deviation, the population standard deviation sigma. Okay, we do the same thing to get the sample variance. But again, the sample variance, we don't use Greek letters. We use regular letters. So we call this S. If you're trying to find this on a keyboard, the way that you would type in a Greek letter is you switch to the symbols on your, you choose, like in Word, for example, you choose that you want to use symbols as your font. And then to get Greek letters, you actually type in the letter S. The Greek letter sigma is equivalent, like where it comes up in the Greek alphabet, as an S. So that's why it works out this way. But so this is S squared. So the sample variance is S squared, which is the sum of x minus x bar squared. Now what's different here is instead of dividing by n, we divide by n minus 1. Okay, so that's why it's important in Excel to specify when you're calculating an average. It doesn't matter whether it's for a population or for a sample, but it's really important in Excel to specify when you calculate the variance or the standard deviation, whether it's for a sample or a population, because of the denominator. So for a sample, the denominator is n minus 1. And then when we take the square root of s squared to get our s, which is our sample standard deviation, it's the square root of x minus x bar squared, the sum of the square root of x minus x bar squared over n minus 1. So to find the sample variance and standard deviation, we first have to calculate the sample mean x bar by summing all the x's and dividing by n. And then we're going to take each x, we'll create a new column in Excel, take each x, subtract off the x bar. Then we're going to create another column where we square that whole column, get another column of squared values. And then we sum those. That's our sum of squared, the sum of x minus x bar squared. And then we take that sum of squares, divide it by n minus 1. That gives our sample variance, s squared. And then we take the square root of that, and that gives us our sample standard deviation, s. So what does this mean? The standard deviation is a measure of the typical amount an entry deviates from the mean. So how much does it deviate from the mean? And the more that it's spread out, the greater the standard deviation. So this first example shows us there's no deviation from the mean. Every single data value is 5. There are 8 data points. So basically our data consists of the number 5 repeated 8 times. So when I take my average, I would add up all of those 5s, 5 plus 5 plus 5, right, 8 times. So it's going to be 40. 40 divided by the number 8 is going to give me back 5. So my mean is 5. And then when I do my standard deviation, each time that I take x minus the mean, since the mean is 5, I get 0. So now I'm going to square that, and then I'm going to get 0 squared divided by 8 minus 1. This is a sample. I think this is sample. And then, so it's a sample because that's s. So I'm going to divide by 7. So 0 divided by 7 is 0. So my standard deviation is 0. So here, now the data is more spread out. And so my mean is still 5, but my standard deviation is 1.2. And here the data is even more spread out because there's nothing in the middle. It's more spread out. My mean is still 5, but my standard deviation is 3. And then the reason this is important is because if the data, and a lot of data is, if it's symmetric and bell-shaped, and you guys have all seen this before, like grades are symmetric and bell-shaped, then the standard deviation will have the following characteristics. About 68% of the data will lie within one standard deviation of the mean. About 95% of the data will lie within 2 standard deviations of the mean. So what this means is if I take my mean and I subtract 1 standard deviation from the mean, and then I add 1 standard deviation to the mean, 68% of the data will fall between those 2 values. So let's say that my mean is 100 and my standard deviation is 10. 68% of the data will lie between 90 and 110. 95% of the data will lie within 2 standard deviations, so between 80 and 120, and 99.7 will lie within 3 standard deviations, which would be between 80 and 70 and 130 in the example that I gave, where the mean is 100 and the standard deviation is 10. Okay, so that's what that tells us. So if the data, again, is symmetric, this empirical rule, which is also called the 68, 95, 99.7 rule, tells me kind of how the data falls. It looks like this. So I want to point out that they left in a really, really important piece off this graph. But so here's my mean x bar. Here's my mean minus 1 standard deviation. So again, in the example I gave, my mean would be 100. My standard deviation would be 10. So this x bar minus, this would be 100 minus 10. This would be 90. And this would be 100 plus 10. So this would be the value 110. So 68% of the data would lie between 90 and 110. 34% of the data here, 34% of the data here. So 34% of the data between 90 and 100, and 34% of the data between 100 and 110. And then 95% of the data would lie within 2 standard deviations of the mean. So this would be from 80 to 120. 95% of the data lies in there. So this is 47.5, and this is 47.5. And since this is 34, and this is 34, this is 13.5, and this is 13.5. So 13.5% of the data would lie between 80 and 90, 34 between 90 and 100, 34 between 100 and 110, and 13.5 between 110 and 120. And then 99.7 is going to lie within 3 standard deviations of the mean. So that makes 2.35%. in here between three standard deviations below and 2 standard deviations below, and 2.35 here. What they left off is the amount that falls beyond this. So there's still 0.15 or 0.3%, which means I have 0.15% below 3 standard deviations and 0.15% above 3 standard deviations. Okay, and that's important because if I want to know how much of the data is more than 2 standard deviations below the mean, I would need to add up the 0.15 plus the 2.35. So the amount of data below 2 standard deviations below the mean is 2.5%, which makes sense because if 95% of the data falls in here, 2.5% is below here, and the other 2.5% that's missing from that is above here. So they might ask you questions on the homework where they have you use the empirical rule. Whenever it says use the empirical rule, you're just going to add up all the percentages to find out what the values or what percentage lies in certain parts. Just remember there's a 0.15 out here and a 0.15% out here on each of the tails that's missing. Right? And then if they give you grouped data, so if they give you like a frequency table, you would still calculate your mean the way we calculate it from a frequency table. And then you would take your X values minus the mean and square those and then multiply those by the frequency. So again, I'll show you guys how to do this because this is the one thing where Excel does not have a formula for it. And you're gonna, if they ask you for this, you're gonna have to do it by hand. So I will show you how to do that. Okay, so let's go look at the homework. Shoot, I think I might have closed my stat lab. All right, so let's go into the assignment. Unit 1, assignment 2. Here we go. All right, and then okay, so 2.3 starts on number 9. Okay, so I am going to skip because these you can figure out from what we talked about with the slides. Number 9 and also number 10 is talking about which way it's skewed. Okay, and then this is the first one where we need to do a calculation. So the number of credits being taken by a sample of 13 full-time college students are listed below. Find the mean, median, and mode of the data, and any measure cannot be found or does not represent the center of the data. Explain why. Okay, so let me copy my data. So I'm going to go open to a clipboard. Always open to a clipboard because if you open in Excel, it'll open a new spreadsheet. I'm going to put this in the chat in Teams so you can copy it. My data for Unit 1, Assignment 2. Number 11. Okay, so that's in Teams, so you can grab it. Oops. Let's see, I didn't put the first 8 where I wanted it to. Be sure that when you grab it, that you grab the first 8. Okay, because it didn't put the first 8 where I wanted it to. All right, and then I'm going to go into, oops, not mean to close that. Okay, I'm going to open up Excel. This is my homework for chapter 2. So number 11 is the data. Right, so here's my data. And then it wants me to calculate where it went. There we go. All right, so it wants us to calculate the mean. So let me start with that. So to calculate the mean, remember that equals the sum of the x's divided by n. Okay, so to calculate the mean, I can calculate the sum of the x's. So let me just go down here to the bottom, or actually we can just do it up here. Okay, so I need the sum of the x's. Okay, so I can go equals sum, and then I can put in, oops, equals sum, put in a parenthesis, and then I can just pick my data values. That's my sum of my x's. I can also just go to the bottom here. Okay, I'm going to put out here sum, so I know what this is. I can just go to the bottom here and I can go formulas, and I can click this auto sum and it sums them for me. Okay, that's 107. Okay, and then the other, so those are 2 ways that I can get the sum. And then the mean is the, oh, let me mark that this was, I pulled this in, so let me go ahead and make this red. Okay, and then the mean equals the sum, oh, let me put in the n. N is the number of data values. So you can get that by counting, right? I can count them, or I can go equals count. And then mark my data. Be sure you don't include the sum. Okay, so I had 13 data points. You can also just count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right, and then the mean is the sum divided by n, or 8.23. Okay, the other way that I can get this is I can go equal average, and then just pick all of the data. Gotta make sure you don't include the sum. And I get the same number. Okay, let me move this down. I'm just going to move this. Control X. I'm going to put this down here. The reason I'm moving that is to calculate the variance. I moved less than I wanted to. calculate, I'm going Control X, and then I'm just going down here and going Control V. And the reason I wanted to do that is to calculate the variance. If I want to use the formula, then I need X minus the mean. Okay, so X minus U. So remember, that's X minus the mean. So it's going to be equals X minus the mean, which we calculated, which was this. So you could pick any of them. So here's my mean. And I am going to go ahead and hit enter so you guys can see it. Okay, so this is 8 minus the mean, and I'm going to anchor my mean. Remember, we put a $sign in to anchor. Anchor my mean. Whoops. And I do that so I can copy this formula. Okay, so those are all my X minus the mean. And then I'm going to do X minus the mean squared. So in Excel, to square something, you're going to use the caret, which is above the 6, to raise it to the power. So I already have my X minus the mean, so I'm just going to go equals this, and then I'm going to square it. So above the 6 is the caret. And then I'm just going to copy this formula. All right. And then the variance for the variance is the sum of X minus U squared. I'm going to put that in a bracket. Divided by N. Okay, because this didn't tell me that this is a sample. Oh, wait, a sample. Oh, it's not asking me to find the variance, but that's okay. We're going to go ahead and calculate that as well. So you have it in your, oh, that's in 2.4. Okay, never mind. We don't need to do that yet. We just need the mean, median, and mode. Let me wait to do this until we get to 2.4. So that's how we calculate the mean. The mean is 8 point. They want it rounded to 1 decimal place. So let me show you in Excel to round to 1 decimal place. If you go here to home and here under the numbers, this changes the number of decimal places. So, oops, that adds. I want to make it smaller. So if you just move this to 1 decimal place, it automatically rounds. So I like to use that to make sure I don't mess up the rounding. 8.2. Does the mean represent the center of the data? So remember, the mean and median represent the center of the data. So even though you get different values for them, the mean and median always represent the center of the data. So I'm just going to say yes. And then the median is, okay, so to find the median, and I shouldn't have done this stuff. We're going to do that on the next set. To find the median, I need to sort the data. Okay, so I'm just going to move it over and sort it. So I'm going to go data, sort. Right, so there's my, whoop. I keep not counting. Let me just do this. So it he's trying to use that 8 as a header. There we go. Okay, now it's sorted. Okay, so the median is the one in the middle. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I have 6 below, 6 above. Here is my median. Okay, so that's one way to get it. The other way to get the median is to use the median equals. So I can go median. Sorry, I go equals, and then I go median. I'm going to hit the tab so it picks up that formula. And then I just highlight the data set. You don't have to have it sorted, so I can highlight my original data. And the median is 8. Okay, so the median is 8. Okay, and then it says, does the median represent the data? So you notice the mean was 8.2, the median is 8, but they both represent the data, the center of the data. Okay, and then the mode is the value that appears the most. So if you look up here, the value that appears the most is 7. It appears 1, 2, 3, 4, 5, 6 times, and 8 appears 3 times. So the mode is 7. And 7 is the minimum value. So the mode is the smallest value, so it's not the center. All right, now it's asking me for the month of April, a checking account has a balance. So this is a weighted average problem. So for the month of April, a checking account has a balance of $533 for 27 days, $2,408 for 1 day, and $200 for 2 days. What is the mean balance for April? So what we put in is the balance, and then we put in the number of days. Okay, so the balance is X, and the days is the weight, right? Because how many days I'm gonna, when I have this balance for a certain number of days, that's what I'm gonna multiply by. So my X values are 533 for 27 days. And then I have 2408 for 1 day. And then I have 200 for 2 days. Okay, and then they want to know what is the average balance. So remember, to get the average, I need to take X times W. So that's equals X times the weight. I'm just going to copy this. Oops. Control Z will undo when I make a mistake. Right, and then my average equals the sum of X times W divided by N divided by the sum of W. I think it's easier just to write. Okay, so I need the sum of W, so I'm going to just put in here and get my sums. The sum of W, I can just go formula and sum that. And I can just copy this over because it'll sum this one. Okay, and so my average is the sum of X times W divided by the sum of W. So my average daily balance is 573.3, round to 2 decimal places. So just in case, I want to make sure this is to 2 decimal places. So I'm just going to move this over to 2 decimal places, 573.30. Okay, only a couple questions left. All right. I think we also did 2.4. This is the variance. All right. So I'm going to skip this one because this one is about the range, which is easy to calculate. It's just the maximum minus the minimum. We're going to do this one. So the depth in inches of 10 artifacts are found and they're listed below. Find the, oh, this is also a range. Complete parts A and B. Find the range. Okay. I'm going to go ahead and do this real quick because I don't know what it's going to ask me next. No, I'm going to skip this one. I want to do the variance. Okay, here we're going to do the range, the mean, the variance, and the standard deviation. All right, so let's grab this data. So this is the data for number 15. There's my data. Okay, so you can put my data into your Excel. I guess you could just type it in. It's not that hard. Okay, and then, so I'm going to go in and do number 15. So here's my data. All right, so here's the data. So the first thing that we need is the first thing it asked me for is the range, which equals the max minus the min. So remember, we can do that by going equals max in the data minus the minimum, the data. So my range is 13. Okay, and then it wants me to calculate the mean. So for the mean, there's two ways I can do it. Mean equals the sum of x divided by n. So that's one way. Let me move this down. So I'm going to insert a line here by right-clicking and just inserting. So I can do the sum. So here we can just auto sum this. So this equals sum of x. Okay. So the mean is going to be 84 divided by the number of data points, which was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, they told us that. 10 football games. Okay, so the mean is 8.4. I can also get the mean by going equals, let me just do it out here, equals average. So if you use your arrow and go down and hit tab and go over, there you go, the average of this, and I also get 8.4. Okay, and then I can do, now that I have the mean, to calculate the variance, so my data, these are x. Okay, so I can do x minus mu. So that's x minus mean, and I need to anchor this. And then I can copy that formula. That's x minus mean. And then I can do, I'm going to copy this over just to make my life easier. And then I need x minus mu squared. So that is this number squared. And now I can copy that formula. And then I need the sum of these. So then I can do my formulas and I can just auto sum that. And that's the sum of x minus mu squared. And then my variance is the sum of x minus squared divided by n. So this is just this value divided by 10. Okay, the other way that I can get that is I can go equals variance. Okay, so notice here when I do var.p is population, var.s is sample. So they're telling me population variance. So population variance is var.p. So I want that one. So I'm just going to hit the tab so it grabs it. And then I can go back and put in my original data. Make sure you don't include the sum. And I get the same answer. So the population variance is 17.24. Oh, it was supposed to be to the nearest 1 decimal. Do that a lot. So this should have been to 1 decimal, so 17.2. Okay, and then the standard deviation, to get the standard deviation, I just did take the square root of the variance. So the square root is SQRT variance. So I'm just going to go equals SQRT and then pick the variance. So that's one way to get it. And the other way to get it is to go equals standard deviation. So do you see the standard deviations here? This one is the population. This one is the sample. So it again, it's asking me for the population. So I want this one. So I'm just going to hit tab. So it'll pick up that formula for me. And then I can put in all of my data points. It's my range. And I get the same answer. Okay, and it wants this one to 1 decimal place. So again, I like to just go here and move this. So I get the 1 decimal place and it's 4.2. Okay, I am betting that this is a rounding issue. And so it probably, let's just try this. It probably wants 4.1. If I take the square root of, I need to put it equal so it knows I'm looking for a form, I'm using a formula, square root of 17.2, it's 4.1. It's kind of annoying. It's supposed to be set up so that it'll take things where you didn't round in between. So sometimes if this happens, and if this happens and you get it wrong, and you calculated it and you got 4.2, just tell me that it counted it wrong and I'll go in and update your grade, especially on a quiz. So you can always show me your work, right? And then tell me, and then I can go in and fix it. And that's it. And that is the end of what you need to do for this week. And then, so you are now ready to complete the Unit 2 assignment, or sorry, Unit 1 assignment 2 homework. And then once you complete that, you will be ready to take your Unit 1 quiz, which covers Chapter 1 and then Chapter 2, Sections 1, 2, 3, and 4.